We'll get started. All right, so here are the results. Just as a average is a P. So that's sort of where things are, just so you kind of get a sense of what the grading scale is for this kind of course. So, you know, some of the things I noticed, of course, the exam was really doable if you had it like that, but if you didn't, oh God, time would not be your friend. So the next exam will certainly be shorter to give people more time to think, because that's clearly an issue here. For some people, I think there is, I fear some of the foundation of undergraduate is not there, and that's something to think about. Making sure if you're going to continue that you really review, your undergraduate course to have that foundation here. There are some things that didn't explain enough, because enough people were confused about this. So I'm going to just want to talk about one very basic fact. Okay, suppose I have 2 point charges, and they're separated by some distance between them. Let's say that there's some x, 1, 2, between these guys. Okay, there's some distance from there to there. And I ask you, what is the potential energy associated with this charge distribution? How would you calculate it? Right. So you can imagine, I move one charge in, it took me no work. Remember, the potential energy of a charge distribution is the amount of work I need to do to assemble that charge distribution, okay? Bringing the charges in from infinity. So I bring the first charge in, it's here. Let's just call this distance x, okay? And then I ask how much work I have to do against the electric field to bring in this charge. How much work is that?
Q1, Q2 over R.
Thank you. Okay? Which is the potential energy stored in the system. I can think about that also as Q2 times the electrostatic potential due to 1 at x. Right? That's equivalent to that energy, because that's how the electrostatic potential is studied. And that electrostatic potential is Q1 over R. Okay? So that's that equivalent. Now, question, does this equal this? Because we said that the potential energy stored in the system is equal to the potential energy stored in the field. Is that equal? No. No. Why not?
To the self-energy.
Because of the self-energy. Thank you, Don. So for point charges, we can't do that, because there's an infinite amount of energy I took to make that, bring nothing into a point. If it was a continuum, right? So here's another question. I have 2 dipoles, electric dipoles, P1 and P2. What is the potential energy associated with, and they're separated by some distance x. What is the potential energy in the system associated with it, what we call this dipole-dipole energy? Well, it's not equal to this, because this thing is neutral. It doesn't have it's got only a dipole, right? So what is that?
PW.
it's P dot E, right? So it's P2 times the electric field due to at 1, right? That's the answer. And so this electric field we found in the first part was 3 P1 minus R hat dot P1 R hat over R. And so there's a dipole-dipole interaction between them, okay? So that was something that got people really stuck. This whole, clearly, that wasn't emphasized enough somehow, the idea of potential energy, but I wanted to make sure we understood the idea. All right? All right, this is my least fun part of being a professor. If I didn't have to do this, which I didn't, but you know, I have to do it. And I want you guys to learn. It's really my hope. I want to do my very best for that. And you know, if you have holes that you need, I can help you find places to fill those holes. For things that you're having trouble with and you can review. And this is only one exam. There's a lot of homework scored. There's another exam, and there's a final. So, but if it really was like, well, maybe I need to go back and review and take this course again next year, think about that too. You think about what's right for you, okay?
Sorry about that.
Oh, yeah, no worries. Oh, I emailed you. You're all set. Yeah, just you email. All right. Very good. All right. So, and who didn't get back their exam? Okay. Hold on.
Which one?
Evan Johnson.
That is me.
I know. And Evan David is somewhere.
Go.
Here you are, you're on top. Who else didn't get back their exam? What's your name?
Wesley Thompson.
Yeah. Wesley. Yeah. Who else didn't get back their exam? Anybody? All right.
Oh, Professor, you
Oh, yeah.
can back somebody else's.
Oh, if I accept, okay. Phew, you don't want to do that. Right. All right. Moving on. All right, so last time we finally got to talk about the full Maxwell equations. So, Maxwell's equations are the whole story in electricity and magnetism. They tell us the field equations. That, together with the Lorentz force law, is the whole story. Okay? So, Maxwell's equations, written in differential form. Let's sketch these into our memory. And importantly, what we talked about is the discovery of the displacement current, which we added to Ampere's law as another source of a curling B is a changing E. Okay? And we have the Lorentz force law, which I can write in full generality in terms of both the current density and the charge density as the integral over all space of rho times E plus J over C cross B. And for a point charge, this is QE plus V over C cross B. Right. So this is really all of electricity and magnetism in these few simple equations. Now, as we were discussing, when we calculated the notion of work done to assemble a charge distribution, that work we do is the force we apply to move a charge against the force of electric fields that are present. And it's not the magnetic field, so the rate at which we do work or I would say this, the rate at which the fields do work on charges. So that rate at which we do work is equal to the sum over all the charges, the force on the charges dotted into their velocity, right? Because the work is F dot dl per dt is the velocity, which is why there's no work done by the magnetic fields, okay? And that's equivalent to the integral of J dot E, because I can write this as QV, which when we write it as a continuum becomes the current, okay? And so this is the rate at which the work is done on the charges. If there's a resistance and there's no energy accumulated, then that work is dissipated. And we call this then ohmic heating. So if I have a steady current, then this is equal to I squared R, which is the power dissipated in the resistor. But generally, this is the work done, okay? And so we can also then interpret minus J dot E is equal to the rate at which energy is transferred from the mechanical motion, or I just say the motion of charge, to the field, because plus that is equal to your exam is emailed to you.
Oh,
Got it. Because plus that is going the other direction. Okay, does that make sense? Right, there's a minus sign there, and that is per unit volume, because this is integrated over volume. Okay. And what we showed last time but this was equal to the partial derivative with respect to time of the energy density plus the divergence of S, where U is equal to 1 over 4 pi E squared plus D squared, which is the energy density in the electromagnetic field. and S is C over 4 pi E cross B, which is the energy current density, having to do with the flow of energy, and we call this thing the Poynting vector. And this equation is sometimes known as Poynting's theorem. So the Poynting theorem is an example of a continuity equation which is about conservation of energy. So let's think about this again, let's review it again, and let's try to understand what this equation means, okay? So let's think again about the general form of a conservation law. Okay? Let's say we have some stuff. The stuff could be charge, energy, momentum, angular momentum, mass. Okay. Kind of an abstract stuff, energy, momentum, angular momentum, but to some degree that's an entity we think of as stuff in the universe. Okay. Now some of this stuff is scalar and some of this stuff is vector. We'll come back to that in a moment. Let's think about scalar stuff like charge or mass or energy. Okay. So if I have some stuff, let me just generically call it Q. It could be charge, but it could be energy, it could be anything, okay? And I want to know something about the conservation of that stuff. The way I think about it is that I imagine I have some volume V, and inside that volume is stuff. And I want to understand how that stuff changes with time. So Q is equal to the amount of stuff inside this volume, okay? And I want to know how it's changing with time. There are two ways that the amount of stuff inside that volume can change. There could be stuff going in and stuff going out. And if that's true, then the stuff inside the volume is changing, unless it's a steady state and there's equal amount going in than out. And we can calculate the flow of stuff into or out of the volume by thinking about a current of the stuff and think about the current density of that stuff, and the flux of that through the surface tells me how much stuff is leaving the surface, okay? If I make the normal out of the surface, okay? So there's an n hat dA here, okay? And so if stuff is leaving, that's going to decrease so this is equal to the flow of Q out of the surface that bounds the volume. Is that clear? We've talked about that in the context of current density, but it could be energy that's flowing, okay? Now, if the stuff can be created or annihilated, then the stuff will just change because it comes from something else. So we can add to this a source term, which I'll call script dr, which is the rate per unit volume at which stuff is created. And then I have to integrate that over the volume. Okay? So, we have conservation laws, thus it can be expressed in terms of a differential form as well. So the amount of stuff inside the volume is the volume integral of the density of stuff, the amount of stuff per unit volume. Okay. And this gives us then what we call a continuity equation, which says that if I look at this for a fixed volume, this tells me that the rate at which the local density of stuff is changing at some point in space as a function of time is equal to, well, I can use the divergence theorem to write this as minus the divergence of J over the volume. That's the divergence theorem, tells us how to relate a flux integral. And thus, this is equal to minus the divergence of J plus script dr. Just because it's true for any volume, the integrands must be true. And this is the differential form of the conservation. It says at any point, the density of that stuff is changing because stuff is converging or diverging from that point, or it's created locally at that point or destroyed locally at that point, and that can also change the density of stuff. Okay, so this is a general form of a conservation law, at least for Q being a scalar stuff. Okay, and so for example, charge. Well, charge is neither created or destroyed, at least non-relativistically. And so we have this term is 0, and we have this, which we often write as d rho dt plus del dot j is 0. Okay? But we also have, for example, energy in electromagneticity. And then we have the energy density written over here. So we have du dt is equal to minus the current density of the energy, which is the Poynting vector, plus the rate at which energy is created locally per unit volume. And the rate at which energy is created locally per unit volume is minus J dot E. So this is Poynting's theorem. It's a example of a general continuity equation where the stuff is energy. Okay? And the flow of energy is related to the Poynting vector. The rate at which energy is created or destroyed in the field is related to J dot E. All right? Very good. So let's do another example of this to see how energy flows in a system in electromagnetism, how we can create or destroy energy. So let's do a little sort of imagined problem. Let's say I have a parallel plate I won't try quite like that, because I need to be able to see what's going on. But I want to imagine these plates are very close together, so that I can avoid the fringing fields that happen. So it's like a capacitor. And what I'm going to imagine is that somehow, some way, I am able to take charge around the perimeter of this little cube, and I'm going to make a current just on the outside. Okay, so I imagine I'm picking up current, picking up charge, and moving it from the perimeter of this conductor, taking it out and putting it onto this. Okay, so that while I'm doing that, at any time, you know, this is a conductor, there's some charge here, Q, as a function of time, and equal amount of charge, equal and opposite minus Q. I'm charging up the capacitor, so to speak, but doing it without a battery. I'm just picking up the charges from the perimeter and moving them along the surface of this, the label of the soup can, and just moving it up there, okay? And I want to know how energy flows in the system as I do this. All right. So what's going on here? Well, as I put these charges up, I'm going to create an E field inside here, right? So inside here, there is an E field, and I am pushing the charges against the E field that is being created as I move them. And so I have to do work. It's just like the Van de Graaff generator, with the hair that I don't have standing on end. And when I turned the crank and I had to pick the charges onto the moving belt, and I'm actually just moving them, literally mechanically moving them. So that's the same thing, and I have to do work to do that, to push against the electric field. And the work I do is J dot E, minus that is equal to the positive amount of energy, okay? So minus J dot E is equal to and if I integrate that over some volume, I could just say this is the rate at which energy is created per unit volume in the field. Now, how is energy flowing in this system? To calculate the way in which energy is flowing, yeah, Donald?
We don't have a J in between the plates, right?
We don't. It's only at the edges that's going to be, it's only there locally that matters. It's a very good point. We'll do that integral, but it's only there on the perimeter where we're actually doing any work, because there's no current anywhere else except on the perimeter. Good. We'll come back to that point in a moment. What's the Poynting vector? Well, the Poynting vector is this. Is there a magnetic field in this system? Well, inside here, I don't have any current. So there's no magnetic field due to a conduction current inside this capacitor. But that's not the only source of the magnetic field. As I'm charging this up, the electric field is changing. It's changing because the charge is changing, and the electric field is growing. And therefore, if I were to look at this capacitor again, I have electric field that's changing as a function of time. And so what direction is the magnetic field inside the capacitor? right? So there's a magnetic field that is curling around this changing electric field by this Maxwell amended Ampere law. What we have is that the closed loop integral of B dot dl around the closed contour is equal to 4 pi over c times the flux of the current through there plus 1 over c the flux of the displacement current, where this is the surface that is bounded by this contour. Okay. Now, inside the capacitor, there is no current. That was the point that Donald was reminding us of. So this is 0 inside the capacitor. So we only have this, okay? And so we can calculate that magnetic field just like we did for Ampere's law when we have a wire with steady current, because by symmetry, if the displacement current is only along this axial direction, and the degree to which I think about it, well, it doesn't even matter. In this case, the degree to which these plates are very close to one another, so this is a uniform field, then I can, I know that this thing is in the phi direction. So B dot dl is a constant, and this is equal to 2 pi r times the magnetic field inside this thing as a function of r. And this then is equal to the rate of change of the electric field times the area, which is pi r squared. Because to the degree to which the electric field is uniform in space, this flux integral over the surface, I can bring this outside, and it's just equal to the area enclosed by this loop at some radius r. This is of course the, maybe I should call it S, because it's the cylindrical radius.
The pi over c term, that's the same thing as like 2 mu naught or something like that.
Yeah. This would be equal to, in MKS units, mu naught times epsilon.
Okay.
All right, so now we know what the magnetic field is on this thing. Let me just get my notes here, because I want to make sure I don't make an algebraic error.
So the pointing theorem would tell us which direction the force would also be in, right?
Well, no, the pointing, this craziness. Anyway, the pointing theorem tells us about energy flow, okay? So it's telling us how energy is flowing. This is the current density. It's the amount of energy per unit time, per unit area flowing in a certain direction. And the direction is the direction of the pointing vector, okay? Very good. So this tells us that the magnetic field is, let's see. So if this is the z direction, then this is the minus phi hat direction because the E is backward. So this tells me that the magnetic field as a function of that radial distance is equal to minus S over 2C times the rate of change of the magnitude of the electric field in the phi hat. It's minus because if I choose the Z direction to be like that. All right, and the electric field as a function of S is constant. This is for S less than the radius of the disk, let's call that radius A, is constant and in the Z direction. Okay, so what direction is the pointing vector? Well, we can look at it for two directions. I mean, it's so much geometry here, right? Over here, the magnetic field is coming out of the board, and the electric field, the magnetic field is coming out of the board right there. The electric field is going down. I say E, but I write E. So E cross B, E cross B. It's radially in. And what about here? B is into the board, right? So then we got E cross B, S. And we can see that from the rules of cylindrical coordinates that S in this case, C over 4 pi E cross B is equal to, in the minus radial direction, R over 16 pi, or 8 pi, d by dt of E times E in the minus that direction. Okay, that's just putting this all together. All right, and that's S. And so I can write this as minus S over 16 pi, the second derivative of E squared. Okay, just d by dt of E squared is twice this. So that's where that factor 2 came from. Very good. So I can, let's see. Now let us calculate the total flow of energy into this volume. Okay, so I want to calculate the flow over the closed surface of S dot n hat dA, where I'm going to take the surface, this closed surface that I want to take as the cylinder whose top and bottom are the top and bottom of the capacitor, and whose side is exactly at the perimeter, but just at R equals, or S equals A, just inside, just epsilon away from the perimeter, okay? So that's going to be equal to, the only contribution of that is on the side, because the pointing vector points in the radial direction, and so it has no contribution of flow out of the top or out of the bottom. It only has contribution. And if we take R hat out, this is equal to the area of the label, which is the perimeter of the label times the height of the label times S. Okay? And so that's equal to pi S at, oh, there's two S's here. That's a problem, isn't that? There's S, the Poynting vector, and S, the radius. It shows that stupid letter. Yeah.
You could put a hat on the pointing vector S.
Yeah, well, this is the magnitude of this, I'll say. At little s equals a, right? Because that's the only place that s is non-zero for the reason that we're looking at the flux at that point. And so that's equal to minus 2 pi a times b times minus that's a plus, a over 16 pi, the derivative of e squared, which is equal to pi a squared d times 1 over 8 pi d by dt of e squared. Okay. And what that is equal to is the volume of this region, which is the area of the cap times its height, that's the volume of that cylinder, times d by dt of e squared, which I say is approximately equal to that. Is that, okay, firstly, why is this approximately and not just exactly equal to that? Well, somehow, somewhere over here, I said this was u, which has a b squared in this, and this just has e squared in that. What the heck happened to b squared? Well, that's a really subtle point. The point is, in quasi-statics over here, that term is higher order in terms of, because, you know, I cheated here, and I made this thing instantaneously, all the charge spread out. I didn't have any way how the retardation effects are neglected. And the B that's coming from a changing E, that's a changing E over C, is a much smaller effect than E itself. So the B inside here is negligible compared to E if the size of this thing is relatively small compared to the time it takes light to propagate across it. So we neglected the B squared term because of the, you know, we don't worry about retardation effects in quasi-statics. Okay? Now I want to do this in a slightly different way. Let's take a slightly different volume. So now I'm going to look at this again. Here's my capacitor with those E and B fields. And now I'm going to take my cylinder that I'm going to look just outside. I want to look at S equals A plus, just outside the perimeter, okay? Instead of just inside the perimeter. So that's, I want to ask how the energy in this volume changes as a function of time, okay? So the amount, the way in which, if I look at the integral of j dot dE over this volume, what is it? Well, as Donald reminded us, the current is only at the perimeter. So the only place we have to integrate is the surface current that's flowing on this thing, right? And what is that going to be equal to in this case? there's going to be current flowing on this thing. There's some charge, the current that is flowing on this thing, integrated over both, over this whole surface, is the current itself. So that's dq dt. This is the current. Flowing. Times the electric field at S equals A. Okay. And then I have to think about, on top of that, the height of this thing times d. So this is equal to J integrated over the volume. Does it have the right units? What's the units of current density? Current per unit area. This is volume. So this times this is current times length, which is that. Okay. What is the electric field? Of course, the electric field is changing as a function of time as I bring the current. What is the electric field between these two plates?
Sigma over 2.
Q equals CV.
Well, yeah, Q equals CV, that's a good one. Q is CV, I like that. That's something we remember. What's the capacitance of a parallel plate capacitor? Well, we have to figure that out. This is equivalent to the following thing. We remember.
2 pi sigma.
What's that?
2 pi sigma.
I'm listening.
2 pi sigma.
Okay, I'm sorry.
Sigma.
2 pi sigma. Excellent. So 2 pi sigma is for a given one, and then I have a second one, so it's 4 pi sigma. So the electric field as a function of time is 4 pi times sigma, which is the charge per unit area. Okay? So if that tells me that the charge as a function of time, and this goes back to the expression that Donald reminded us about, the capacitance is equal to the area over 4 pi times the electric field. Okay, if I divide this by D and multiply this by D, this is the voltage and this is the capacitance. But I'm going to just write Q of T here is equal to d by dt. I have the, and the Q we already said was A over 4 pi times the electric field as a function of time. That's the charge times the electric field. Which is equal to the area is 4 pi a squared times d over 4 pi d by dt of E times E, which is equal to the volume over a pi d by dt of E squared. So we have again Poynting's theorem, which tells us that the energy that is created at the perimeter is changing due to the increase as we do the work we do to push the charges on the perimeter. That creates an electric field inside this capacitor, and the work we did in moving that charge is equal to the energy we created, which is the volume times the energy density. Okay, so it's all self-consistent. Question: what happened to the flow of energy for this cylinder just outside? Where's S, the Poynting vector in this case? Why isn't that? I thought that was part of the equation here. The electric field is 0 outside to the degree I ignored the fringing fields, right? So that's all self-consistent in that way. All right, very good. So this is an example. These are the kind of thing you have also in your homework coming up. Right, okay. Other stuff. So we talked about stuff. We have, oh, where is our stuff? Oh, there's our stuff. We talked about charge, we talked about energy. We're not talking about mass because that's about mechanics. We need to think about these guys. So, if we want to think about the continuity equation, for a vector quantity, let's say we have some vector A, and I want to know how that quantity changes as a function of time. The thing about a vector quantity is it has not only a magnitude but a direction. So I have to think about that. And one way to do that is to think about a continuity equation for each component. Say, Cartesian component. So I can think about the rate of change of some component of that thing by the continuity equation that we have over here is equal to minus, and I'm going to call this thing, well, let me do it this way, J of that, but it itself is a vector. Think about what this notation means in a moment. Let me just write this plus the rate of creation of that component. So this is a continuity equation for one of the components of A. But that thing, whatever it is, say the x component of momentum of the field, could be flowing in a different direction than x. There's like this vector, it's pointing in that direction, but it's moving in that direction. Or it's pointing in that direction, and I'm moving in this direction. That's a tensor.
Oh.
A tensor is a thing that has multi-components that are, so I can think about Tij, let me call this thing T, as T sub I dotted into E sub J. It's the component of this flow along the component J. Okay? So I can rewrite this in a vector notation where T is a tensor the rank 2 tensor, that describes the flow of A in some direction. And that direction of flow need not be the same direction as A, which is why it has two components. One component tells me how much of that stuff along that, and J is telling me the direction which is flowing. All right? So let us look at an example. Momentum. Okay, momentum is a vector. And we can ask about the rate at which fields change the momentum of the charges. What is that? The rate of change momentum is force. And what is that equal to?
Equals MA.
Well, F does equal MA, but particularly for electromagnetics, what is the force that is exerted on the charges? The Lorentz force, which we can write in full generality like this. And I'll define this as the force density, which when I integrate over all space gives me the force that the fields exert on the charges, or the rate at which momentum is imparted on the charges by the fields, which means that minus F is equal to the rate at which momentum per unit volume is transferred from charges to the field. Is that clear? Because plus that is the rate, is the opposite. It's the rate at which momentum is transferred per unit volume from the fields to the charges. So this we would call, this is equal to that. That's the source of momentum in the electromagnetic field per unit volume. This is the rate at which momentum is created in the electromagnetic field. Electromagnetic fields have momentum. There's something called radiation pressure, right? There is a force. You remember photons have momentum, right? That's the Roy, it relates the wavelength to the momentum. We'll come back to that, okay? So this is the conservation law. So now we want to express this in terms of an equation just for the fields in the same way that we did here. So here we had something about the energy density and the flow of energy given this rate at which energy was transferred from the charges to the field. Now we want a similar equation which gives us an expression for the momentum density in the field, the amount of momentum per unit volume in the electromagnetic field, and how that momentum is flowing. And the way in which that momentum is flowing is a tensor. known as the Maxwell stress tensor, which stresses everybody out when you see it, okay? So, yes, Donald?
So we're using a tensor because for a given direction of momentum, we could have the momentum from there being redirected into any of the other
That's
two
correct.
directions plus the one it's already in.
That's right. So you have a vector quantity, but it could be flowing in a different direction. Okay, so mathematically, the way we do this is that the local charge and current densities are related to the local derivatives of the field through Maxwell's equation. So Maxwell's equation tells us that the local charge density is equal to 1 over 4 pi del dot E. And the local current density, if we solve for Ampere's law, is equal to, let's say, over C, is equal to 1 over 4 pi del cross C minus 1 over 4 pi C dE dt. Right? So now I can plug that back in for F, and I get 1 over 4 pi, the electric field times the gradient of the the divergence of the electric field. That's this first term. And then I have plus del cross B crossed into B from this first term over here, the 1 over 4 pi. And then I have minus the E dt with the 1 over C, let's see. J over C is equal to 1 over C cross B. Okay, that's this. Okay. And this thing is equal to the time derivative of E cross B minus cross into the B dt. Just using the product rule. Right? But what is the B dt? It's related to del cross E. Right? So dB dt is equal to minus C del cross E. So let's put it together. The algebra on this is not so important, but we'll just do it a little bit more and then we'll skip to the end. What we have is F here is 1 over 4 pi E times del dot E. I'm going to cheat. Oh, let's not cheat yet. We'll cheat in a little bit. Plus E cross del cross B. That's from this term. Oh, there's a minus sign over here. So that's a minus. Now I'm going to cheat. And write this as B times del dot B. Why can I do that? Why can I add that term?
Zero.
Because del dot B is 0. So it's convenient to have it there. And then I also have a minus B cross del cross B. Okay, and then I have this last term over here, which is minus 1 over 4 pi c E cross B times. Okay. So I'm going to put a minus sign on everything over here, because this is equal to what we just said is the rate of creation of momentum per unit volume in the electromagnetic field. And what it equals is the following: d by dt g plus the divergence of, I'm going to say, minus t. Where g is defined to be equal to 1 over 4 pi c E cross B, or the Poynting vector divided by c squared. And t, that tensor, is equal to 1 over 4 pi E outer product E plus B outer product B minus a half E squared plus B squared. Okay. So let's, this you could see, right? That's this term. The fact that when I take the divergence of this, I get this, it's a pain in the ass. There's so many lines of algebra. Believe me, it's true. Yeah.
So that Maxwell stress tensor there, right? That's
Oh, I didn't, it should be, I didn't finish that.
Okay,
Shit.
yeah.
Thank you. Thank you, Krista. Yeah, excuse me. Okay. Let's look at this and interpret it and understand what it means based on this. Okay? Right here. Oh, there's no minus sign there. Hold on a second. Or check one of my signs because I confused myself about them. Oh yeah, good, that's correct. All right, I did it right. So, looking at this, what we had before is that d by dt of rho stuff plus del dot j stuff equals the r stuff, where rho is the density of stuff per unit volume, J is the current density of the stuff, and R is the rate at which stuff is created or destroyed per unit volume at a particular point. Yeah, Donald?
The stress tensor has a trace, right?
No. The tensor itself has components. So Tij over here is equal to 1 over 4 pi Pi Dj plus Bi Dj plus a half E squared plus B squared delta Ij. These are, you can think about it as a 3x3 matrix. These are the components of the matrix, okay? So the tensor has 9 components. It's not an irreducible tensor. Let's say Lefty.
It's not irreducible because you have to be traceless and symmetric.
Yes, right. This is not traceless. Okay, so I want to come back to the most important points here. What is G from this equation, given its relation to this? What's that? It's the momentum density. So this is the momentum density. So if I integrate over all space, this is the momentum in the field. Okay. What is minus T? T is the stress tensor, and minus T, according to this equation, is then what?
Momentum current.
So momentum current density. It's telling me how momentum is flowing. Okay? And F, which is given here, or minus F, is telling me something about how momentum is being transferred from the field, from the matter, from the charges to the field for it's the local source of momentum. So the point here is kind of the following. Let's suppose I have 2 point charges. Okay, let's say that they're opposite, right? We know that there's, in some sense, I can think about there's action at a distance where this charge exerts a force on this charge and can change its momentum. It could start to move, right? I can think about that as action at a distance, or I can think about it as momentum is transferred from the particle to the field, and then the field transfers the momentum to the particle. So that everything is local. It's the field that carries the momentum, and that carries it. There's no action at a distance. There's nothing over here that affects something over here instantaneously. If this thing starts to move, the fields are going to change. And that change is going to cause radiation, and that radiation propagates. And when that radiation propagates, it's carrying the momentum away from the particle and bringing it from this particle to the other. Everything that we think about in the universe happens locally. There is no action here that affects anything there that cannot be causally connected to it. The way the forces are exerted is locally through the fields. And that is expressed in this crazy continuity equation. We could, and you can look at the notes, I don't fully encourage you, but at least to glance at it, to write down Coulomb's law as the flux of the stress tensor through a closed surface. I can make a hemisphere, I can put a plane here, make a hemisphere, and then calculate the flux of the stress tensor through this surface, and you'll find that momentum is transferred through that flux. It's like a fluid stress. Okay? But we would never do Coulomb's law that way. The last thing I want to just conclude in my 4 minutes of grace time is about angular momentum. So angular momentum is about how much, the rate at which I create, let's say it this way, the rate at which angular momentum is changed on the charges due to the field is called torque, right? Torque is the rate at which angular momentum is changed. And the torque is equal to the position crossed into that. That's now angular momentum. And so this is the equation of motion. Conservation of angular momentum. Yeah.
Is that a vector crossed with a tensor?
It is, which is another tensor, which dotted into a vector is a vector. So this is a vector, this is a vector, this is a vector. This is a tensor. A tensor dotted into a vector is a vector. Everything's a vector. You can write it out, as you should, in its components. See how that works. But the physics point I wanted to emphasize is that the electromagnetic field can carry angular momentum. I could have for example, and you're going to see this in your homework, right? So the angular momentum in the field is coming from the fact that if I am going to twist around this cylinder, as in problem 2 of your homework, there's a charged cylinder, and I'm twisting it around, and as I do, there's a back EMF. So I have to apply extra torque to keep that thing moving. And when I apply extra torque, I've put in extra angular momentum above and beyond the angular momentum that went into the charges moving themselves. Where did that angular momentum go? It went into the fields. Okay? So the fields carry energy, they carry momentum, and they carry angular momentum. And we can think about that as that angular momentum, energy, and so forth as being transferred back and forth between the matter and the fields. The matter can put those physical quantities into the fields, they carry them over to the other thing, and they can absorb it, and that's how it works, right? And when we think about the quantum version of that, that means that the quanta, the particles, the fundamental, I love the word corpuscular parts of the field, we can think about them as having energy and momentum and angular momentum. The photon carries energy. The photon carries momentum. The photon carries angular momentum. Now there's another kind of angular momentum which is not part of classical electromagnetics, which is spin. That's not, the angular momentum here is the orbital angular momentum of the photon. The photon could go in a trajectory like this. If I have a vortex-like wavefront, I could have a ray, if I twist an optical fiber, the photon has angular momentum. That's its orbital angular momentum. It also has intrinsic angular momentum, which is its spin, but that's not part of this story. All right, very good. That concludes our discussion of the conservation laws, and next lecture we'll start discussion about electromagnetic radiation.
Is that compared to a